I have been using this for the last, God knows, 10 years. This is a PP bar collision which took place in Day-5. But let us forget it, the physics is the same. Details are different. So here is a proton and an antiproton colliding. And these red lines are the partons. That is, the basic thing, the core thing is a parton from the proton and an antiparton from the antiproton. They collide and you have two outgoing partons. In our example it was TT bar. So we were busy with these red lines only. But there are lots of junk and that is real life. The first thing of course is that you will never see a B quark or for that matter any quark in practice, because we learned that quarks are always confined. So in practice what will happen is this quark will soon hadronize, but this hadronization is not an easy thing, it is a very complicated thing and let us see what it is. Okay? But one thing you should be careful about at the very outset, that this whole thing is a non-perturbative process. Confinement itself is a non-perturbative process and therefore there is no way you can calculate it perturbatively. So what you have to do is you have to introduce hadronization models, which are normally called in technical terms the fragmentation model, and see from experiment whether your model of a quark hadronization agrees with real life thing. So let us see what it is. Now of course here, and it is that. What happens is, suppose we are focusing on this quark, then this is the hadronization. This region is called the fragmentation region. That is, see, these are all magnified. So it means that immediately upon production, the quark do not hadronize. It takes a little bit of time, which is typical type of time of strong interaction, let us say 10 to the minus 22. Okay, 22 seconds. After that, the quark will start hadronizing. So what will come out is a stream of hadrons which are confined in a very narrow core. Now here comes a completely different brand of physics. In practice, of course, what you are doing is a very simple event generation in a hands-on section. In practice, you will use a program which is much more complicated and which will do this hadronization for you. So you put a cut on the PT of the jet, that is the streams of hadrons within this pore. You put a PT cut or a rapidity cut again, not for the quark you cannot see, by the way. Is there any exception? Does this hold for all quark? The key is 10 to the minus 22 or 23 if you like, or even 21 seconds. The top quark. What is the lifetime of the top quark? If you calculate it, it will still be 10 to the minus 24, 25 or something, some such numbers. So a top lives too long compared to the time of hadronization. Therefore, this guy decays exactly like a free particle. Nobody has seen a top hadron. It decays like a free particle, but then the problem is not solved because it will always have another quark in the decay product and that fellow will hadronize. Okay. So the problem is not over, but it is good to remember that the top quark do not hadronize. Alright, so rest of the figure is simple. Now, so this is a non-perturbative complication.
So that the signature of top in the decay.
Weak wall. You do not see the top.
The decaying part.
Weak wall. And of course isolated leptons and so on. What about the lower one? Now this is a complication due to perturbative tucity. Now one thing I could not discuss throughout is the asymptotic freedom of tucity. Now some of you may have heard it, some of you may not. The idea is that just like electrons can radiate protons, quarks can radiate gluon. I have heard that. The trouble, however, is that if the gluon radiates, the coupling constant here is important. Right? Now the electron charge you know. Now if in a LHC calculation you put in the electron charge, you will be committing a small error. You will be committing error, small error. But you will be committing a large error if you put some theoretical value of the strong coupling constant, because it is momentum dependent. If the momentum is large, it is small, therefore you can apply perturbative calculations. If the momentum is small, you cannot. This is basically what is happening in the case of this jet formation. This hydrogenation is mostly low momentum phenomena. But again then the complication is that although you are very happily calculating this part with some jet formation technology, once in a while a gluon will pop up either from here or from here or from here or from here, and you will have extra jets in the event. So when you calculate the cross section or the probability of the event, if you want to have good accuracy, then you must include a hard gluon emission and calculate it in your d sigma, in the cross section, okay, not as a peripheral complication, it is part of your cross section, and as you take more and more gluon into account, the cross section becomes more and more difficult to compute. But this part of the complication is at least in principle calculable. Okay. You need smart calculators, real stout ones, but it is a complication.
And this initial state radiations?
Coming. These are hard gluon radiations. They are part of the matrix element. Alright? Now let me go back to, of course the gluon eventually will hadronize, and then there are models of jet formation from the gluons. They are also available. So that is not very difficult. But can you see the level of the complication? That is, sometimes, as Professor Agarwal was telling, that this fellow is emitting a gluon which is not a part of the matrix element. Now, qualitatively, this means that this is not really a hard gluon, but sometimes it could be a hard gluon. Again, the emission is Bremsstrahlung. So normally you will have relatively soft gluon emission. Once in a while you have a hard gluon emission. Now when you do a cross-section calculation, you do it only for a hard gluon, which will show up as a hard jet. Now this fellow will normally be soft, but not below the threshold of observation always. That is the trouble. And once in a while, with very small probability, it will be hard. Okay? Now, how do I handle this?
So origin of these ISRs are
Radiation, gluon radiation from the quark. But you have to understand the difference between the two. So I'll do it again. Suppose you are talking about a genuine hard gluon radiation. Know what it means? It means that it is coming from the matrix element, and whatever is the probability given by your quantum mechanics is the probability of radiating this gluon. So this is observable as any other. Alright? But this fellow is normally expected to be soft, most of the time unobservable. But since you are doing a model calculation, this is the so-called the pattern shower Monte Carlo. That is, this fellow is coming from here. Sometimes it can be hard. Sometimes. Now, when you do a cross-section calculation, you have then two distinct animals. One is genuine hard gluons coming from the matrix element calculation, and one is a initial state radiation gluon, which is sometimes hard, in fact hard with low probability. Now the point is, when you are generating your events, okay, and you are doing a calculation where you have not only the parton, but parton plus a radiation. So let me try to draw it. So now here there is no calculation, so make sure that you understand the concept, because then you can see something very useful in the hands-on section. So this is a matrix element calculation, but you want to be very accurate, and you put a gluon there. A gluon is being radiated. It could also be radiated from the final state. Then I am not worried. The trouble, however, is that you are using an event generator where you want to take this also. Alright? Now suppose you don't do it. Suppose you do only the parton level. So this is the key part of that. Then your event generator will generate such things, gluons. And you have no conceptual problem. Because if your event generator is good, you will get a good representation of this ISR gluons. If your event generator is bad, you will get a bad representation. It is not your problem. But when you are taking this as well as this, then you have a conceptual problem, because somehow you have this in the lowest order diagram here, but suppose they are in the same phase space, then it means that they are the same one. So you are making a double counting. You are putting a gluon here, you are putting a gluon here. It's a, you are counting the same gluon in the phase space twice. So this is called double counting. Okay. If the ISR photon, ISR gluon is weaker than this typically, then it is not a problem. Then it is enriching your cross section, and you have to take it whatever your model gives. Therefore, you have to avoid this double counting, and this is called matching, and its main signature is, if you don't do matching, you will get more jets because you are making double counting. If you do the matching, that is, if you drop the possibility of double counting, then you will get smaller number of jets, and you have to see data which one is better description, and it turns out that the matching always gives you a good result. The good thing is that although you have not learned about matching, the exercise that you are doing is has this matching provision, and you can simply do this, that with matching you get more jets or more events if you like. If you drop matching, you get less jet in the final state. So this is a real life phenomenon.
So ISRs are mainly before collision, and FSR is after collision. Now, since your detector can see both of them, if they pass your trigger, you have to isolate, because these are ISR should not be part of your calculation.
No, why not? Why not?
All this
After
happens when
collision.
there is
No, it's nothing. I mean, that's an event with a more jet. Why do you want to throw it away? See, if a guy can radiate, it will radiate during the actual experiment. Why do you want to throw it away? It is genuine. The only thing is you should not count the same jet twice. That is the trouble. For example,
Oh yeah, I will take into account the event, but I need to make sure that I am not double counting the jet.
that is matching. That is matching.
Otherwise,
That is, you are taking the same jet once in the higher order calculation and once in the lower order calculation as a ISR jet.
the sum of these two lines, these pink lines, can look similar in my detector.
That is not a problem. Final state radiation is not a problem.
I think he is talking about separating the jets from the hard starter jets.
Right, because after all, I am
That
seeing,
you
I
cannot
have
do
a camera, I am
experimentally.
seeing them.
No, you cannot do
Cannot
this
do it.
experimentally. How can you do it? Experimentally you will see jets.
Right.
Typically the jets will be softer if it is ISR
ISR
FSR jet, but since this is quantum mechanics, there is a good probability that one of them could be hard and then it could be a problem. Because if you do a higher order calculation, then they fail. See, in terms of alpha, number of coupling constants, these and that are same,
Same.
right? Now, if you don't do this calculation, then you will say that I am a poor man, I cannot do higher order calculation, but I have a pattern shower model. So I am taking some effect of the higher order into account. Not the full, not through the matrix element, but through a model. I am taking into account. But now you are ambitious and you have done a higher order calculation and you want to add both. Then people will say that okay, add, but be careful. Because once in a while your pattern shower model will also give a hard jet and then there is a chance of double counting. That means your experiment may not, see, experiment do not know whether it is coming from matrix element or what.
Okay.
But if you make a double counting, your result will not agree with the data. That is the trouble. So there is a prescription which is named after Michelangelo Mangano. There are others also. But this MLM matching is very popular. So the thing that they are using in the hands-on session has this MLM matching. And that can be. Alright, I think, do I have anything else in my basket? I don't think so. More pictures here and there. But yeah. So I think that's it. So at last I am at the end of this whole business. It was very enjoyable but a little tiring also. So I am happy that I have done to the best of my ability. Whether you are happy or not, I don't know. But let us say goodbye at this. Oh, you may have questions. So, questions. Alright then, if not, then because I have to catch the train.
Sir.
Huh?
No, then we can talk later. I had a question.
No, but
No,
we have time, sir.
If it is a 2-minute question, yes.
I will
If it is a half an hour question, we don't.
So we have 10 minutes.